Hello, in this video we'll design the multi-cycle controller for the other instructions besides load word. So just as a review, so far we had a state machine with all these 5 states to do load. First we fetch the instruction and add 4 to the program counter. Then we decode the instruction, read the registers and the immediate. We calculate base address plus offset to get the memory address. Then we read the memory, and then we write back the result to the register file. So a store starts out in the same way, the same first 3 steps. We fetch the instruction, decode it, and we also need to calculate the address. So this arc we will do for stores as well. So if the op is either 3 or this one for store word, we will, in either case, add base address plus offset. But now the 4th step is different for a store. In the 4th step, we want to write a value to memory. So here's the data path while doing that. In the 4th step, the address was sitting here in ALU out. We need to make result source 00 to choose that address. Bring it back around and address source to be 1 to provide that address to the instruction and data memory, just like in a load word. But the difference is this time instead of reading we want to write. So the value we want to write is sitting on write data from the register file. We provide that back to the data memory, and now we need to assert memWrite to make the write take place. So that's the 4th step of store word, and it completes the store word. So at the end of either load word or store word, we have an arc back to the fetch stage. So once we finish the instruction, we go and we fetch the next instruction and keep running. Alright, next up, let's take a look at R-type instructions. So on the 3rd step of an R-type instruction, we need to do the ALU operation. Remember, the R-type instructions are add, subtract, and or set less than. So for any of these, the first source comes from register file port 1. So ALU source A needs to be 10. The second source comes from register file port 2. So source B needs to be 00. We go to the ALU, and we need to look at the instruction to know what to do. So ALU op of 10 meant looked at the funct fields to determine the operation, which kind of ALU operation it is. We get our answer out, and we store it in ALU out at the end of the 3rd step. Next, we need to write that answer back to the register file. So after the execute step, we go to the ALU write back step. In the ALU write back step, we have our value sitting in ALU out. We want to choose it with the result mux, so result source needs to be 00. We bring it back around to the register file, to the write data port. The destination register is coming from the instruction, and we need to assert reg write to tell the register file actually to do the write. So that completes the R-type instructions. Finally, let's take a look at branches. So on a branch instruction, we need to calculate 2 things. One is the branch target address, which is PC plus the offset, and the other is RS minus source 1 minus source 2 to see if the 2 sources are equal. So notice that the ALU wasn't being used in the decode stage. So we might as well take advantage of it being idle then to calculate the target address, which was the PC plus the immediate. Now, we're going to do that no matter what instruction we're doing, because when we're in the decode stage, we haven't even decided what instruction it is, but none of the other instructions needed the ALU in the decode stage, so we might as well take advantage of having it. So let's add some more control signals to state 1, so that while we're reading the registers, we're also calculating the target address. So here we are in the decode state. The old value of the program counter is sitting in this register. The immediate is available here, but assign extend the immediate. make ALU source B 0, 1 to choose the immediate, make ALU source A 0, 1 to choose old PC, and tell the ALU to add. So ALU op is 0, 0, meaning add, and that will calculate PC plus the offset and put the result in ALU out. Next, we need a third state for branch on equal. So when the instruction is branch on equal, we'll go to a state where we compare the registers, and if they're equal, we take the branch. So to compare the registers, now in this third step, we have our two register values sitting at the output of this flop. We'll select the first one by ALU source being 1, 0, source A. Source B needs to be 0, 0, also to select. Bring those to the ALU. Need to tell the ALU to subtract. So ALU op should be 0, 1, which makes ALU control 0, 0, 1, which makes a subtraction take place. ALU computes the result that we don't actually care about, but it also produces the 0 flag that we do care about. That 0 flag goes back to the controller, and we assert the branch signal. So you may remember from the controller, if branch is true and 0 is true, then PC write gets asserted, and we will write the program counter with our branch destination. The branch destination we obtained because the PC plus offset was sitting in ALU out after the decode step. So we make result source 0, 0 to choose it, bring that around. Now that's ready here as PC next for the program counter, so that if we do write it, we write the branch target address into the program counter. And that concludes our controller for the multi-cycle processor.